Welcome to MRS Bulletin's Materials News podcast, providing breakthrough news and interviews with researchers on hot topics in materials research. My name is Laura Lay. Around 60 years ago, a theoretical limit was set for the movement of dislocations in materials. Modelling and atomistic simulation work has suggested that this limit may not be strictly true. Now, for the first time, experimental work has shown that the simulations are correct.
The question was, can dislocations propagate faster than the sound wave speed? Even in textbook, it is written that these dislocation velocities do not go over the transverse wave speed of material.
That was Dr. Kento Katagiri from Stanford University. His interest is in laser shock compression, where a high-intensity laser causes compression of the material. This leads to extreme pressures greater than a terapascal. His research has shown that the sudden shock imparted by the laser means that dislocations are transonic. In diamond, they travel faster than the slowest transverse sound speed.
So it is known dislocations cannot travel at sound wave speed. If you slowly increase, this sound wave speed becomes a barrier, and we cannot overcome. But if you use a shock wave, because of the shock wave front is a discontinuous wave with the strong energy jump, it can actually jump to the transonic region.
But Dr. Katagiri's team looked at diamond, a highly stable material that doesn't undergo phase transformation, allowing them to look at purely plastic deformation. His team used an X-ray free electron laser, also known as an XFEL, to collect data from the diamond as it was hit with an intense shock from an additional drive laser oriented at 90 degrees from the XFEL beam. The XFEL was important as it produces intense, short pulses of X-rays to collect frames of data from a single shot of the laser providing the shock. The femtosecond pulses of the XFEL are necessary to see the ultrafast phenomena that occur on a tiny scale.
Laser shock community has usually using something called velocimetry, which uses an optical laser, green light laser, and irradiate from the other side of the drive laser to track the speed of these wave fronts. So in this case, we are pretty much the first one to apply X-ray radiography on laser shock compression experiments to visualize something behind the wavefront.
When the diamond was oriented so that the shock from the drive laser travels down a certain crystallographic axis, remarkably clear V-shaped bands were observed. These shapes correspond to stacking faults. Compiling data collected with a time resolution of femtoseconds allowed the team to determine the velocity of propagation of these features and figure out that they are moving at 16 to 18 kilometers a second, firmly putting them in the transonic region. To collect these data, the team made some innovations. Usually, a CCD, or a charge-coupled device, is used to collect images that result from the XFEL beam passing through the sample. But this type of detector would be damaged because it needs to be located close to the sample, and therefore close to the shock laser. Instead, a new detector that uses a lithium fluoride crystal was developed, which makes use of colour centres that form in its structure as a result of the XFEL beam emerging from the sample of diamond. To help visualise the results, the sample also had to be carefully aligned.
I wasn't expecting to see these lines, and somehow I just came up with an idea of rotating the crystal 90 degrees. It was lucky to find these V-shaped lines, and the idea was we aligned these strip planes along the FEL beam.
The propagation of waves through a material is familiar to disciplines such as geology and seismology, but Dr. Katagiri's work is most applicable to extreme shock events such as missile strikes and shuttle launches where pressures of 1 terapascal or more might apply. These pressures can also occur inside stars or during meteor strikes. The results are relevant to a type of nuclear fusion known as inertial confinement fusion, which uses intense lasers to compress the fuel. Now that one theoretical limit has been exceeded, Dr. Katagiri wants to push things even further.
The question is, where's the top limit? Is it actually the longitudinal wave, or is there another thing above the longitudinal wave in the supersonic region or not?
This work was published in a recent issue of Science. My name is Laura Lay from the Materials Research Society. For more news, log on to the MRS Bulletin website at mrsbulletin.org. Follow us on Twitter at MRS Bulletin. Don't miss the next episode of MRS Bulletin Materials News. Subscribe now. Thank you for listening.